Hi, I'm Seemakhupt. I'm going to talk about our work, PMNet, a system that accelerates update requests by persistently store data in network. This work has been done in collaboration with Sihang, Yasas, Senevirathne, and Samira from UC of Virginia, and Shahbaz while he was at Stanford. Let's get started. For the summary of this talk, we start with an observation that data center application usually store data in separate storage server and manage data to network. Update request latency slow down client, and in network compute reduce read request latency but not update requests. Our key insights are: first, maintain persistent state in network by adding persistent memory to network device. And second, persist update requests in network to move server off the critical path. We propose PMNet that locks requests in persistent memory in network and use locked requests in order to recover from failure. We also integrate PMNet with replication and read caching. We implement PMNet on FPGA and evaluate whole system. Result shows that PMNet improves both throughput and tail latency over client-server baseline. First, I will talk about the motivation of PMNet. Common applications in data center store data in separate server. For example, the front end of social networking and online transaction processing, such as banking application, access storage backend, such as Memcached and Redis. The latency of accessing data in storage server is critical to performance of these applications. For example, in this banking application, it wants to pay me $10. The banking application sends the request to update the balance of A and B on storage server and wait for the response in order to ensure that the server processes and persists the update. Only after the server responds, the client continues with the next operation. Therefore, update requests are latency critical. Now, we want to see what happens when the client sends the request. The request is forwarded to network stack of the client, to network, and enter the network stack of the server. Then the request is processed by the server, and the server sends the response to the client. The breakdown of update request latency shows that most of the latency is from the server side. However, there are an existing approach that mitigates server-side latency. First is in-network compute that adds application logic in network device to reduce the latency of computing tasks. Another is by passing multi-cache in network to serve read requests. In-network cache moves server latency of some read request critical path. However, because failure can happen while the request is being delivered to the server, for update requests, the client waits until it receives the response from the server because it needs to ensure that the result of an update is persistently stored on the server. Thus, in-network caching lacks persistent storage and cannot move update request latency off the critical path. Next, I will talk about the key idea of PMNet. To reduce the blocking time of update requests, PMNet adds persistent memory to network device. Persistent memory allows network device to persistently lock update requests. Here's how PMNet persistent locking works. Upon receiving an update request from the client, PMNet locks the update request in persistent memory. After the request persists, PMNet sends ISCA to immediately unblock the client. Then PMNet forwards the update request to the server. The server then processes the request of the critical path. Therefore, PMNet enables sub-RTT data persistence in network. However, there are challenges for persistent locking. First is how to recover lost packet when failure happens. For example, after the client sends an update request, PMNet locks the update request and sends the ISCA to unblock the client. Then failure happens before the request arrives at the server. Since the client is unblocked, it cannot receive the packet. In order to recover a missing request, first, the server detects a failure using timeout or heartbeat signal. Then, server sends retransmit request to PMNet device. PMNet device read locked update request in persistent memory and resend it to server. The server then processes the request normally. Therefore, PMNet recovers lost requests from persistent lock in PMNet network device. Next challenge is how PMNet ensure that requests are executed in server in correct order. First, I will talk about requests from the same client. For example, when the client sends 2 requests, the requests can be reordered in network. To maintain ordering from the same client, PMNet client adds a sequence number to each PMNet packet. The server can then use the sequence number to correct order and process requests in order. Another issue with ordering is ordering across multiple clients. For example, when 2 clients want to update a critical section, first, both clients send a lock request to acquire a lock on shared server. However, lock request persists in PMNet, and PMNet sends ACK to respond to the client. After both clients receive the ACK, both clients enter the critical section. This is wrong because only one client can enter the critical section. To solve this problem, synchronization primitive such as lock request bypass PMNet. In this case, lock request is forwarded and processed directly on the server. Therefore, only one client acquires the lock and enters the critical section. Note that even though lock requests cannot benefit from persistent locking, update requests within critical section can still benefit from shorter latency, and bypass requests are not frequently used. Next, we talk about PMNet design, how PMNet enables in-network persistent locking. For the design, I will talk about 2 parts. First, PMNet hardware pipeline, and second, PMNet protocol. For the hardware pipeline, traditional programmable network switch or NIC, packets are forwarded to the destination according to rule programmed in the match action table. On the other hand, PMNet NIC or switch adds lock queue that buffer requests from MAT pipeline to the persistent memory that store locked requests. Thus, in addition to forwarding incoming packets, PMNet match pipeline also control access to the persistent memory. For PMNet protocol, PMNet is built on top of UDP protocol by reserving a specific UDP port. PMNet header consists of 4 fields: type that determine different PMNet packet type, session ID that's used to separate different PMNet sessions, sequence number that's used for ordering, and hash value that's used to index requests in PMNet device. PMNet device perform different operations based on type field that define the packet type. We will see how PMNet handles each packet type. For update requests, PMNet first log update request in the persistent memory. After the request persists, PMNet sends ACK to unblock the client. And at the same time, PMNet forward request to server. Therefore, PMNet logs and forward update requests, and PMNet send ACK to unblock client once the request persists. For ACK packet, PMNet removes associated entry in persistent memory and forward the ACK to client. For retransmit requests that server send when the server is recovering a missing packet, PMNet looks up lock requests, read lock requests, and resend requests to the server. For bypass packets, such as synchronization primitive, PMNet forward requests directly to the server. Apart from logging update requests to move server off the critical path, there are additional applications of PMNet. Those are accelerating replication and serving read requests with caching. Next, I will talk about PMNet integration of read caching and replication. For replicated server without PMNet, when primary server receives an update request, it replicates the request across all replicas. Only after all replica finish processing the request, the primary send the response to the client. We can see that replication increased latency of an update request. In order to accelerate replication, PMNet locks update requests in multiple devices to protect against hardware failure. In this example, with two-way replication on the server, update requests are also locked into PMNet devices. When client sends an update request, the request is locked in PMNet device. The client waits for the ACK from both PMNet devices. This ensures that the request persists in both PMNet devices. Then the request is forwarded to the replicated server of the critical path. We can see that PMNet moves the latency of replication of the critical path while offering the same level of protection as on the replicated server. For the integration of read cache, first, PMNet locks incoming requests and forward to the server. Upon receiving read request, PMNet looks up requests in persistent memory. And if lookup is a hit, PMNet uses locked request to respond read request. Otherwise, PMNet forward read request to the server. Thus, PMNet uses locked update request to accelerate read request. For the evaluation, we implement PMNet on Silent Autoscale Plus evaluation platform. We program match pipeline on the FPGA and use DRAM to emulate persistent memory. We use QSFP port as network interface. For the design point, we implement PMNet as both as bump in the wire in server NIC and as a bump in the wire in server rack Tor switch. For the first experiment, we want to see the performance of PMNet device. We use ideal handler on server that immediately respond to requests. The graph here shows bandwidth and latency of an update request. Y-axis shows latency and x-axis shows the bandwidth. The red line shows the latency and bandwidth of baseline client-server setup. We can see that the client-server baseline achieves maximum bandwidth around 10 gigabit per second, which is close to the line rate. While blue line shows latency bandwidth of PMNet in switch setup, we can see that with PMNet in Tor switch, maximum bandwidth is the same, but with considerably lower latency. While dashed line shows PMNet in NIC configuration, which has similar performance to PMNet in switch. Therefore, both PMNet device configuration offer the same benefit of lower latency and same bandwidth as client-server baseline. We refer to PMNet in switch only as PMNet for later result. Next, we evaluate update request performance of real application. This graph shows the latency distribution of update requests in Redis. X-axis shows latency of update requests and Y-axis shows CDF of the request. The red line shows the latency of baseline client-server setup, and blue line shows the latency of PMNet setup. We show Redis workload as example due to space limitation. Other workloads follow similar trend. We can see that for Redis workload, PMNet decreased tail latency of update requests by 4.5x. Therefore, PMNet significantly improved tail latency of update requests. Similarly, we evaluate performance of mixed read and update requests in 50-50% ratio. We can see that while half of requests, which are update requests, are accelerated by PMNet, read request performance remains the same. Thus, PMNet without read caching only improve read update performance. On the other hand, with caching shown in yellow line, PMNet improves performance of both read and update requests. For replication, we compare the performance of baseline client server with and without replication, with PMNet with replication in both PMNet and on the server, and PMNet without replication. This graph shows the latency of update requests normalized to client server baseline without replication on Y-axis. The results show that PMNet with replication reduced update request latency by 5.9x over client server with replication, and the performance penalty of PMNet replication over PMNet without replication is minor. Therefore, PMNet moves replication of the critical path while maintaining protection against hardware failure. For more detail, You can see the full result in the paper. Next is the conclusion. For the conclusion, PMNet locks update requests persistently in network device to move server off the critical path and use locked requests to recover from failure. PMNet can also integrate with replication and read caching. We implement PMNet on FPGA and evaluate whole system. PMNet improves update throughput by 4.2x and tail latency by 3.2x on average over client-server baseline. PMNet with replication improves replication latency by 5.9x on average with same level of hardware failure protection. And with the integration of read cache, PMNet improves mixed read update latency by 3.36x on average. We will also make implementation of PMNet publicly available soon in the link here. Thank you.